Okay, so in this video I'm going to take a look through the section A of a paper 3 specimen paper 2. So we're looking at the practical skills, that kind of thing. So we're going to look at how the magnetic flux density around a current carrying conductor varies. So this looks very much like the search coil experiment that you do as part of the course. So you've got a circular frame which we've wrapped a coil of wire around, so essentially it's wrapped around like this, and it's mounted inside a rectangular frame, and then we've got a search coil in the middle that's connected to an oscilloscope so we can measure any EMF that's induced in it. So the student clamped the search coil so it's coaxial with the circular coil. So essentially that means the area of the you can see for the coil is essentially parallel to the area of this one. And then it's connected to a signal generator. So the coil is connected to a signal generator, so there's an alternating current and therefore an alternating field around the big coil. And then we're going to get an EMF induced in the search coil, and we're actually going to get maximum EMF induced at this position. So we're going to see that then displayed on an oscilloscope. Okay, so the first question, we want to determine the frequency of the current in the coil, and we've got a time-based setting. So essentially we're going to want to measure as many time periods as we can. So we've got one time period, 2, 3, 4. So essentially that is going to be, so if we're going to measure, well, let's do this in red so you can see it. So essentially that's where I'm going to start, and I'm going to that same point on a wave much later. So that's 4, so let's count the number of squares between there. So 1 square, 2, 3, 4, 5, 6, 7, 8 squares, and then there is 0.25, 0.5, 0.75. So there's like 8.75 squares, and each square it says is 0.2 milliseconds. So 0.2 times 8.75 gives us a time period of 1.75. Divide that by 4 because we want the time period for one cycle, and then 1 over that, and you end up with something in the range of 2,285 using that method. So let's actually show that working. So the time measured was 8.75 squares, I reckon, times by 0.2 times 10 to the minus 3. So the total time I've measured there was 0.2 times 10 to the minus 3. It's 1.75 times 10 to the minus 3. So from that we can get the time period for 1, because I measured 4 cycles, so divide that by 4, it gives you 4.375 yada 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 times 10 to the minus 4. So frequency is 1 over time period, so that 1 over that comes as 2,285, so that will be 2.3 times 10 to the 3 hertz there, to an appropriate number of significant figures. Okay, so then using figure 2, determine the root mean square voltage of the EMF induced in the search coil, our Y gain being 10 millivolts. So what I'm going to do is measure the peak to peak. So we can see the peak's here, and the other peak is here. So 1 square, 2 squares, 3, 4, 5, 6. So it's 6.75 squares. So that peak to peak is 6.75 times by 10 times 10 to the minus 3, because it's in millivolts. So let's calculate that. So 6.75 times 10 times 10 to the minus 3. It's going to be like 0.00. So I'm not sure why I used my calculator there. 675 volts. So the RMS, so to get just the peak, we would divide that by 2. So to get RMS, we divide by root 2. So we're going to divide the whole thing by 2 root 2.
divided by 2 divided by root 2, and that will give you the RMS, which is 0.0238. So let's give it, let's give that as 2.4 times 10 to the minus 2 volts there. Okay, so in the mark scheme for this question, for some reason it gives 24 millivolts, but just be careful because it says give the units of volts, so make sure you do adjust for that. Okay, so figure 3 and figure 4 show the search coil and the flux density peak produced by the current in the coil. And we're looking at it from above, so we're looking down on the apparatus. So this is the field created by our the current in the big coil, and then we've got our search coil area is essentially across here, and our big coil is going to be much bigger across here. Okay, so when it's arranged in figure 1, we're looking at figure 3, and then we're going to change it to by an angle theta to see how it changes. So we're just going to rotate the whole coil with respect to the search coil there. Okay. To explain why the flux linked with the coil is directly proportional to the cosine of theta. The flux linkage is essentially affected by the area of the search coil that is perpendicular to the field line. So if we rotate the search coil through an angle theta, the area perpendicular to the field is now calculated using a cosine theta there. So let's write that down. All right, and so just to illustrate what I was talking about, if this is the field and this is the angle, this is where the search coil is, the area of the search coil is A, but we want the area perpendicular, so if it's an angle theta here, it's essentially going to be a cosine theta to it. So that's essentially how that works. Okay, so let's move on to the next one. So they've clamped the rectangular frame so it remains vertical, and they haven't changed the position of the search coil, but you rotate the coil, the coil you've got creating the field around, which is probably different to how you did it in the experiment. You probably adjusted the angle of the search coil instead. And the time base is switched off because you're only interested in the EMF really. And then you've got the vertical line displayed on the screen. So the Y gain stays the same, and the length of the vertical line and the angle is recorded. So we've got this. Plot on figure 6 a graph to test if this data confirm L is direct proportional to cosine theta. Use the additional column to calculate it. So the first thing we're going to do is calculate all of the cosine thetas, which we're going to do to 2 significant figures because all the value is 2 significant figures. Okay, so that is all the values calculated. Just had a look at the mark scheme. Some absolute joker has said you can give these to 4SF. 3 I could just about accept because it's 1 more than the angles, but it should really be 2. Whoever wrote the mark scheme frankly needs a good shooting. Anyway, so let's continue on and plot this on the graph. Okay, so then this is the graph with the points plotted. So I'm afraid this software doesn't allow me to draw lines of best fit very straightforwardly, but what I do is I draw a straight line that extrapolates back, and we can see that this graph is a straight line through the origin, so that's going to tell us this is the directly proportional graph. So let's do that part. So right, so and that's our evidence as a straight line through the origin saying that it is. Let's continue with question 1. Okay, so when the time base is switched off, this is the trace we get on the oscilloscope. So that's this trace right here. So describe 2 adjustments the student should make to reduce the uncertainty in L, referring to specific controls on the oscilloscope. So the first thing, we're going to want to measure the peak to peak. So we're going to want to move it over to this line here, which is one of the options on the scale called the X shift. So we're going to want to move it this way using the X shift, and we're also going to want to move it down so the middle of this line is at the origin. So we're going to use the X and the Y shifts there to do it. And if we can, we'd like to adjust the Y gain to stretch it out even longer but stay on the screen. So that could also be an option, but the biggest thing we need to do is shift it so that the center of this line moves to the origin here. Okay, so that's what we've got here. So in each case, we've identified the specific thing we'd use, so the X shift and the Y shift, and what we're trying to do with that, we want to move it to the Y axis, and we want to then make sure it's centered on the Y axis, because that's going to make it easier to take measurements and make those measurements more precise and more accurate. Okay, so the student adjusts the signal generator so the frequency of the current in the circular coil is doubled. State and explain any changes that should be made to the settings of the oscilloscope so the experiment can be repeated. So if you double the frequency, you double the rate of change of flux linkage, so you're going to get double the EMF induced. So the change we're going to have to make is we're going to have to double the setting on the Y axis. So if it was 10 millivolts per centimeter, we're now going to have to make it 20 millivolts per centimeter because the line is going to be twice as long. Okay, so that's what we've got there, and you see I've linked in Faraday's law to actually explain what's going on, because it wanted us to state and explain the changes we would make, and the change you make is to the Y gain, so you're doubling the Y gain. Okay, so that completes 1.7. Let's go on to 1.8. Okay, so we finally reached the last part of this question. So the apparatus is rearranged so that both coils lie in the same vertical plane and are coaxial along the line PQ. So as this is when it's at the center of the search coil and then it's moved over here. The values of L corresponding to different values of X are recorded. A graph of this data is shown in figure 9. Okay, so this is figure 9 with this graph. It is suggested that L decreases exponentially as X increases. To explain whether figure 9 supports this suggestion. So to be an exponential relationship, the half-life should be constant. So we're going to need to measure a few half-lives. Okay, so let's start at 4.5. So we need the time for it to get to 2.25, which, if we go across, and then we read down, is about here. Then we need 2.25 divided by 2. We need to get to 1.125, which is essentially here. If we dot across, dot down, we should say we started along this line. Ooh, went a bit wonky there. Right here. It's gone a bit all over the place. So it's starting to look like our half-life is constant, but let's just check with one more. That's going to be 0.56. It's about here. So let's have a look at the half-life in each case. So this is 25.5, that's 19.5. So we've got a half-life of 6 in here. That one is 13, so 19.5 minus 13.5 gives you a half-life of 6. And then here, 13.5 minus, what's that, 987, gives you a half-life in there of around 6.5. So the conclusion is the
lives are approximately constant. So, can't spell constant. The relationship is exponential. So that is your conclusion there. Okay, so that finishes question 1. Okay, so for question 2, we've got a temperature sensor connected with a data logger to monitor the temperature of a fixed mass of recently boiling water over time with an interval of 600 seconds down there. And unsurprisingly, we've got a graph that's a curve following Newton's law of cooling there. Okay, so these next questions require use of the graph, so I've done that and I've just come out with the answers. So first off is just about reading a value of your graph, so going to T is 190, reading off the temperature and giving an answer. So I got it as 61.0 when I did that. You need to make sure you go to the 0.0 because that's the scale of your graph. Next, once to determine the gradient of the graph at T is 190. So what you need to do is draw a tangent to the graph at T equals 190 and make the tangent nice and long so you can do an 8 centimeter by 8 centimeter gradient triangle on it. And when you do that and work out its gradient, you should get something around this number. So you'll get some slight variation depending on your line, but you get something similar. So this is my gradient. So then we want to use that to work out room temperature. So we've been given some more data and the equation to calculate room temperature. So we need our first gradient, which was minus 0.0960 times our second temperature, 46.6, minus our second gradient, which is 0.0645 times our old temperature, 61.0, all divided by minus 0.0960 minus 0.0645. So let's calculate that. So 0.0960 times 46.6 times minus 1. It's 0.05 times 61. 0.0. And that comes out as a value of 17.111, blah, blah, blah. So we're going to give that as 17.1 degrees because all of the numbers used to calculate it are 3SF. All right, let's continue with question 2. It can be shown that when a hot object at temperature theta is allowed to cool in a draft, the rate at which the temperature decreases is directly proportional to the temperature difference. That is Newton's law of cooling. The rate of cooling is equal to the difference in temperature. The student realizes that theta minus the room temperature will decrease exponentially with time and designs an experiment in which 2 temperature sensors are connected to a data logger. Sensor 1 is placed in a beaker of recently boiled water. Sensor 2 measures the air temperature in the room. The data logger is programmed to record the output from the sensors as the water cools for 600 seconds. That's what this graph is. So we've got the room temperature measured and we've got the temperature of the water. Okay, so the theta minus theta r will decrease exponentially in the same way that the potential difference across a discharging capacitor decreases with time. When a capacitor discharges, the potential difference across the capacitor falls to 1 over E, an initial value in a time called the time constant. Electronic engineers assume that a capacitor becomes fully discharged in a time equal to 5 time constants. Estimate the time taken for the water to cool down to room temperature. So essentially what we're looking for is what 5 time constants of our graph are. So first of all, let's find out what our time constant is. So I reckon that graph starts at 88.5, and we reckon the room temperature, if we look at it, starts at 21. So the initial temperature difference is this. We need to divide that by E. So 88.5
minus 21 divided by e to the power of 1 gives you 24.8. So then the so essentially after one time constant, that's equal to that. So the theta itself will be that plus 21, which is 45.8 degrees. So we can get one time constant, where if we go to 45.8 on our graph, so 45.8 and read down, I reckon that is 390 seconds, which means that the time taken is going to be 5 times that. So that 5 times 390 to 1950. So that's going to be 2.0 times 10 to 3 seconds to 2 significant figures there. Okay, so let's see how we go with that. So let's move on. Okay, so another student carries out the experiment using the same equipment, but we've got a different sensor shown here. So what I'm seeing here is when you get a sensor looking like this, that means the sensor doesn't update very often. So essentially your sensor is updated here and it has this reading, and then it updates, what is that, 20 seconds later. So this is only actually updating every 20 seconds, whereas the one previously would have been updating much faster than that, which is why the curve looks smooth. So digital equipment, the graphs always look like this, but if you make the update rate quick enough, you can't see the stages. So it wants to account for any differences between these results, and they are the way they are displayed with those shown in figure 11. So in figure 11, we started at 88.5. We can see here we start at 86.5. So that's the first thing. Let's account for that. So our starting temperature is greater. Okay, so let's have a look at the time it finishes being. Oh, let's just group those together so it doesn't go wandering. Okay, so let's have a look. So at 600 seconds, we can see this one is at what's that, 35, 36, 37, 38, 38.5. On the original graph, it finished at 35. So we've got a different temperature here. So let's record that. So from this, we can see the rate of cooling was smaller. So either the room temperature was higher or the draft acting was lower. And the final difference I already spoke about was to do with the sample rate of the sensor. The sample rate in figure 12 is a sample every 20 seconds. The sample rate was much higher in figure 11. Okay, so that would complete my answer to that question. Let's move on to question 3. Okay, so a student carries out an experiment to determine the diameter of a cylindrical wire based on the Young double slit experiment. So what we've got here is we've got our source of light. We've got this object here, which is acting like our double slit, and we get an interference pattern. All right. Okay, so it says A and B act as coherent sources, which is why we're getting an interference pattern between P and Q on the screen. The student uses a meter ruler to measure the distances L and D shown in the diagram. Okay, yep. And figure 14 shows the interference pattern between P and Q. And they use a vernier scale to indicate the positions of the centers of 2 of the fringes. And we've got those measurements here. Okay. So determine the spacing of the interference fringes using figure 13 and the data in the table, giving your answer to an appropriate number of significant figures. So what we're going to need to do is R2 minus R1. And look how many spacings that represents. Well, it represents 6. So if we put in the values that we've got, so R2 is 11.16, R1 is 8.71, divide that by 6, and that gives us 0.408 and that's measured in millimeters, and we're going to give that to 3SF because the 6 is an integer, so the significant figures are determined by this one, which is 3SF. Okay, so that's the spacing. So determine the diameter of the wire if we've got this wavelength. So you should know this equation. And we said the cylinder is acting essentially as a double slit. So S is going to be lambda d over W. And we've got the wavelength is 589.3 times 10 to the minus 9. We've just worked out W, it was 0.408, blah, blah, blah. And we've got the distance, it's been given to us, so that's 0.395. So let's do some 589.3 times 10 to the minus 9, divided by our answer, times 0.395, gives you 5.70 times 10 to the minus 4 there. So that would be your answer in meters, because we converted all into meters. So estimate the number of interference fringes seen between P and Q. So we've been given the distances that we need. So essentially, if we look at the, so we're going to get D over L should be equal to the distance PQ over D plus L, because what we're looking at is essentially a triangle that keeps on going. So you always get this relationship with those kind of triangles. So we know D, we know L, we know D plus L. So PQ is going to be D times D plus L over L. So we know D was, I forget, we've got that answer, it's stored in my calculator still. So we've got 5.7 times 10 to the minus 4. D is 395, L is 46. You notice I'm not going to bother with the millimeters because it's going to end up with a ratio anyway. Alright, so let's calculate this value, which is 5.4 blah 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 times 10 to the minus 3. So the number we're going to see is going to be PQ divided by the spacing between them, which was like 0.408. 0.408. And then times by 100, because it was actually, sorry, times by 1,000 even, because it was in millimeters for that one. And we get 13.39, so we're going to see 13 fringes essentially there. So that's going to be how many spacings, which, and if you're going to see 13 fringe spacings, you're going to see 14 fringes there between them. Okay, so the student uses a micrometer screw gauge to confirm this result for D. Describe a suitable procedure the student should carry out before using a micrometer to ensure that the measurements are not affected by systematic error. So the first thing is you need to make sure you close the jaws fully, and then you need to check that the reading says 0 when you've done that. Okay, and in case you're wondering what a ratchet is, it's the twisty thing at the end of the micrometer. So to reduce the impact of random error, the student takes several measurements of the diameter at different points along the wire to get a mean value for D. We've got those measurements. Use the data to determine the percentage uncertainty in the data. So we're going to need to essentially find the biggest and the smallest. So there is your biggest value, smallest is this value. So what we're going to do is we're going to do the uncertainty, which is the range divided by 2. So that's 0.574 minus 0.566 divided by 2, giving you an uncertainty. So we haven't got the percentage uncertainty, we've got the uncertainty, which is 4 times 10 to the minus 3, and that's going to be measured in millimeters. Okay, so once we've done that, what we need to do is work out the value to use, which will be the average of all those values, which I've calculated as 0.570. So your percentage uncertainty is going to be 4 divided by the average, which is sorry, it's 4 times 10 to the minus 3, sorry, millimeters, by our average, which was 0.570 blah blah blah, times by 100%. So it's 4 times 10 to the minus 3 divided by our answer times by 100 gives you 0.70%, giving it to 2SF, because that's what we always do for percentage uncertainties. Okay, so that completes this section of the paper. I also have a video reviewing the turning points section of this, because that's the board that we do at my school. So do check that out if you do turning points. And if you have any questions about what I've done here, please do comment and let me know. I'll be happy to answer those for you. But thanks for taking the time to watch.